Okay, Physics 221. So this is chapter 38, we're starting quantum physics. And I have to warn you, quantum physics is very, very mathematical. So just be ready for it. So again, this is part of what we call modern physics. Relativity is part of modern physics. Quantum physics is part of modern physics. Quantum physics basically showed that you can't use classical physics to describe tiny, tiny things like atoms. It just doesn't work. So that's why quantum physics was developed. Okay, here we go. So we're going to understand the photoelectric effect experiment and its implications. We're going to spend a lot of time here. We're going to go in gory detail. And the reason is because we're going to first discuss it classically. And then we're going to discuss the data, and we're going to realize that the classical explanation has nothing to do with the data. It can't explain the data. And the only way you can explain the data is by learning quantum physics, right? And so this is like one of the pivotal experiments. So we're really going to go in gory detail. And we're going to learn a new model of light. So we learned the wave model of light. Then we learned the ray model of light. Now we're going to learn the photon model of light. We're going to review the evidence for matter waves. Yeah? Matter waves like electron waves. And the de Broglie wavelength. Recognize that the de Broglie standing wave of a confined particle requires energy quantization. We'll explain it, don't worry. Then we'll talk about Bohr's model of the atom. We'll use the Bohr model to explain things that we talked about in chapter 37 or 5, I don't know. Remember that chapter we spent just like an hour on, where there's no homework? And then we're going to look at the Bohr model of hydrogen. Now, before I do this, I found some quotes about quantum mechanics, which I just think are really interesting. So I want to go through these quotes. Kind of long. These are long, but it's kind of cool. So these are all quotes about quantum mechanics. By the way, quantum mechanics is just quantum physics, right? The physics of tiny things. Because quantum mechanics predicts such a wide variety of phenomena so accurately, quantum theory is probably the most successful scientific theory ever invented. Its practical impact extends to every device or idea that depends on the details of the microscopic world. Electronic devices such as transistors, silicon chips, integrated circuits, all the information and communication technologies such as TV and computers and cell phones. Most of modern chemistry and some of biology, lasers, and our understanding of different types of matter ranging from superconductors to neutron stars and nuclear physics, nuclear power, nuclear weapons. Central to the entire high-tech world is an elusive and highly non-Newtonian particle, the electron. So he's basically saying that the electron is not, you cannot consider the electron a classical particle. It just doesn't work that way. Quantum mechanics is the strangest field in all of science. From our everyday perspective of life on Earth, nothing makes sense in quantum theory. So basically nothing agrees with our common everyday experience. Okay, Niels Bohr was one of the, he helped develop quantum physics, and he won a Nobel Prize for that. Anyone who has not been shocked by quantum physics has not understood it. That's a good one. Okay, Feynman, he basically came up with his own way of doing quantum physics, and he was also a Nobel Prize winning physicist. Atoms are completely impossible from the classical or Newtonian point of view. Completely impossible. They wouldn't last more than like a few millionths of a second. So you need quantum physics, right? Okay, here's Feynman again. I think I can say, no, okay, hold it. He was a theoretical physicist. He came up with his own way of doing quantum physics. He was a genius. He got a Nobel Prize, all right? I mean, he's a genius. Now, let's see what he says. I think I can safely say that nobody understands quantum mechanics. I'm going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. And that's quite a statement from Feynman, right? Okay, this is Gell-Mann, another Nobel Prize-winning physicist. All of modern physics is governed by that magnificent and thoroughly confusing discipline called quantum mechanics. It has survived all tests, and there's no reason to believe that there's any flaw in it. We all know how to use it and how to apply it to problems. So we have learned to live with the fact that nobody can understand it. And here's another one. Regarding quantum mechanics, we must let go of all our preconceptions about the world derived from our experience and senses, and instead let mathematics and experiment lead the way. That's how quantum physics was developed. Experiment, mathematics. Experiment, mathematics. Forget about common sense and everyday experiences. Kind of like relativity, you know? All right. Okay, so here we go. So now we're going to talk about the photoelectric effect in gory detail. And you have to pay attention, because after I spend about, I don't know, 20 minutes or more describing it, you are going to have to draw a diagram which you basically summarize everything I've said. So you really, really have to pay attention, all right? Okay, so here's a vacuum tube. It's a tube that's been evacuated from air. It's a vacuum tube. Okay, it's a vacuum tube. And this is a hot metal cathode. And we can adjust this temperature. This is called the anode. And it's these far away. And we're going to have, these are electrons. And here's a battery, which we're going to ignore for now. And here, this is, I stands for electrical current. This is something that measures the current. I think that's all you need for now. Okay, so again, remember, forget about the battery for now. All right, let's talk about this hot metal cathode. Okay, piece of metal. Well, what do you have in metal? You have electrons, right? Electrons are free to, you know, you talk about the sea of electrons in a metal, right? Because a metal is a conductor, so the electrons can flow, you know, if there's a battery connected to it or something. But anyway, so here we have this hot metal cathode, and we have these free electrons, right? Sea of electrons. Okay, now, at normal everyday temperatures, the electrons are bound to the metal, right? You don't see electrons just zipping off all over the place. So at everyday normal temperatures, the electrons are bound to this piece of metal here, this cathode. Okay, so that's fine. At normal temperatures, the electrons in the metal are bound to the metal. Now, here's something that we're going to talk about a lot, a work function. So the work function is E0. It's energy. It's the minimum energy required for these electrons, for an electron to escape. So in other words, if we heated this thing up and the electrons got enough energy, they could escape. So the work function is how much energy they would need to escape. Okay, fine. Now, when we heat the metal cathode, obviously we're increasing the electron's thermal energy, right? Thermal energy. Okay, that makes pretty good sense. Now here's something that's important. Okay, hold it, sorry. When we heat the metal, the electron's thermal energy increases. That means that their kinetic energy increases, right? Okay, so their thermal energy increases as well as their kinetic energy. Now, the important thing is there's not going to be just one value of the thermal energy for all of the electrons. There's not going to be just one value for the kinetic energy of the electrons. They're going to be spread out. We're going to say they form a distribution. Okay, there's a physics word for you. All right. So the kinetic energies and the temperatures, the thermal energies and the kinetic energies, they follow what's called a Maxwell-Boltzmann distribution. You don't have to know that, but that's what it's called. Okay? So this is the number of molecules, or let's just say, well, just pretend this is electrons, okay? Same thing. So number of molecules and the speed. So you can see, you know, that the temperatures and the speeds, they're distributed, right? There's not just one value, okay? So for this particular temperature, look, some are going slowly, then faster, 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 you know? So all I'm saying is that there's not going to just be one temperature. There's not going to be just one amount of thermal energy. There's not going to be just one amount of kinetic energy. They're going to be distributed. Okay, so the distribution of the thermal energy implies a distribution of kinetic energy. That just means there's going to be different values of the thermal energy. There's going to be different values of the kinetic energy. That's all. Okay, whoopee. All right, now, at sufficiently high temperature, in other words, if we get this hot enough, some of the electrons are going to have enough energy that they can escape. So that means that their thermal energy has to be greater than the work function, right? Because again, the work function is the minimum energy needed to escape. So if that thermal energy is greater than this, then they have enough energy to escape, so they're going to escape. All right? Now what's the energy left over? It's the kinetic, you know? So the kinetic energy of the electrons equals the thermal energy minus that energy that they had to overcome to escape. So kinetic energy equals thermal energy minus work function. That's kind of a big deal. So kinetic energy equals thermal energy minus work function. All right. Okay, so here's a question for you. So let's say there's no battery. So in other words, this is neutral. Okay, this is neutral. So we're heating this thing up, and the electrons are getting enough energy to escape. So if there's no battery, the escaping electrons will be emitted at different angles, so they travel in different directions, or will they be emitted at the same angle, so they travel in the same direction? So pause your video and think about it. Okay, you're back. It has to be different angles, right? I mean, this is not charged, and so, you know, there's no reason for the electrons all to go to the same direction. They just go wherever they jolly well feel like it, okay? So basically, no battery, neutral, so there's no attractive or repulsive forces or anything, right? So the electrons just go wherever they feel like it, right? They go different angles, so they go in different directions. Okay, now, so that's just a summary of what I said, right? Just a summary. Yeah. And this is all purely classical, right? This is all classical. Okay, I hope you're paying attention now, because you're going to I got about 10 more minutes, and then you're going to draw a very important graph. All right, so that's all classical, okay? We still want to do some more classical, all right? Now we're going to put a battery in. Now, if you don't know, if you didn't take 220, shame on you, just kidding. But so here's a battery. So that means that this is going to have a negative charge. And so look at the battery. Delta V is positive. That means that this is negative, this is positive. So this is charged negatively, this is charged positively. We're going to reverse them in a minute. But for now, we're saying delta V is positive. Negative, positive. Okay? So now obviously the electrons are going to be attracted to this, right? I mean, that's the important thing. That's the big deal. Okay, so if you have a battery with this polarity, right, so that's positive, what are the electrons going to do? It's sort of obvious, right? Electrons are attracted to the positive anode, right? Right? Opposite charges attract. So you don't even have to vote. I'm just going to tell you, right? So if the voltage is positive like this, the electrons are going to see this positive plate and you say, oh, white! And so, you know, they might have been going this way initially, but they're going to be attracted to this, okay? So if delta V is positive, as shown, the escaping electrons bend toward the positively charged anode because unlike charges attract. Okay, that makes sense, right? That makes totally sense. And you know, it's not going to take a very high voltage. You just make this a little bit positive, and almost all of the electrons are going to be attracted to this positive anode, okay? So nearly all of the electrons are going to bend towards that anode. Okay. Now, let's do this one. If delta V increases, but the cathode temperature remains the same, what's going to be true about the, this is classical, right? What's going to be true about the current? So pause your video and think about it. So we're going to increase the voltage, but we're going to leave the temperature of the cathode alone. What's going to happen? All right, so number 3. It's going to briefly increase. The current's going to briefly increase because, you know, there were some electrons that didn't quite hit this. But if you increase that voltage, basically all of the electrons are going to hit this now. And the current is the motion of electrons. And so, you know, it's going to increase just briefly. Because, again, some of these electrons that didn't hit it, now they will hit it, right? So you get a current. But then it's going to stay constant. Because remember, what has to happen to kick out the electrons? The energy, right? I mean, the temperature, well, it's energy, right? You have to increase the temperature here to kick out the electrons. Because you're only going to get electrons kicked out if the thermal energy exceeds the work function. Okay, so the brief increase just means, like I said, the electrons that miss this, which is a really small percentage, but after you get them all, then it's going to be constant, right? Because the temperature is the same. Okay, now, keep paying attention. Now look what we did, or look what we're going to do, right? So here, it's minus plus, right? Minus plus. So that's positive. Now we're going to reverse the polarity. So switch your battery around, right? So now it's plus minus. Okay? So now this is negative. Well, what happens to electrons? Are electrons attracted to a negative metal? No, they're repelled, right? Right? Same charge repels. So now these electrons are going to see this guy and they're going to go, oh, I don't want to get near that, right? All right, so now there's a repulsive force here. Okay, so if delta V is less than 0, as shown, what will the escaping electrons do? Well, I just told you, right? Number 2, they're going to bend away, right? They're going to bend away because like charges repel, unlike charges attract. Okay, now, do any of the electrons reach the anode? Now remember, let me give you a hint. Remember, some of the electrons have super high kinetic energy. Some of them have, you know, there's a distribution. Remember, there's that distribution of kinetic energies. Some have low, some have high. Most of them have like an average, but, you know, but there's some, you know, real go-getters, right? So do any of the electrons reach the anode? So there's a real safe answer. There's a safe answer. It depends, right? If you ever get interviewed by somebody and they ask you a question that's really difficult to answer, just say, it depends. Then move on. That's what politicians do all the time. Anyway, it depends. Well, what does it depend on? Well, it depends on delta V, right? I mean, if this is just a little bit negative, you know, then maybe the really fast guys will reach it. If this is super negative, then even the fastest guys will be repelled. So it really depends on how much negative this is. So it depends on delta V, okay? It depends on delta V. And I mean, and here's an analogy, you know, let's say I throw something up. Well, you know, if I just throw it with like a, you know, medium kinetic energy, it's not going to reach the top. But if I throw it with a lot of kinetic energy, if I throw it with a lot of kinetic energy, it's going to reach the top, right? So that's kind of an analogy, you know. Okay, so I mean, but you know, I mean, think about it. Because this is negative, all of these guys are going to be slowing down, right? Because of the repulsive force. But the really, really fast ones, you know, really, really fast ones might reach it, or maybe will reach it, you know. Okay, however, you know, I don't care if I'm throwing something high, you know, if the roof is, you know, like a mile high, I don't care. I'm sorry. I can throw it as fast as I want, but I'm not going to reach it, right? So that's kind of like the same thing here. I don't care how fast these guys are. I mean, you know, they're not going to go, well, if I make this thing super, super negative, even the fastest one is going to be deflected or stopped. Let's just say stopped. Okay? So here's a big deal. So delta V equals minus V stop. Stops or deflects the fastest electrons. So what we're doing is we're defining V stop. So it's kind of funny that I don't know why, but they define V stop to be positive. So we're saying when delta V equals negative V stop, we're stopping or we're deflecting, well, really stopping the fastest electrons, okay? So if we get this thing super, super negative, those guys cannot reach it. Stop. All right? Now, here's something that we're going to use again. So remember that chapter where we talked about the spectra, you know, different wavelengths, absorption, and all that thing. And then we talked about units, electron volts, and all that. And I said we were going to use that in quantum mechanics. Well, here's our first time. So we learned about electron volts. And so what we're saying here at V stop, we're saying EV stop equals K max. Right? So that's just energy conservation. Remember, electron volt, that's an energy, right? So if you take the voltage, multiply it by the charge of the electron, that's an energy unit. And so we're saying that at this voltage, that's the maximum possible energy of the electrons. Okay, that's kind of a big deal. Okay, I hope you're still paying attention. All right, so EV stop equals K max. All right, here you go, guys. So now, this is what I promised you. So I want you to draw a current versus voltage graph for the situations just discussed. All right? Good luck, right? So I want you to label V stop. And remember, V stop, so delta V equals negative V stop. All right? So V stop is a positive thing, but there's no current, right? There's no current when delta V equals negative V stop. Okay? So you know it's going to start out here. Anyway, so pause your video or maybe rewatch it or something, but this is important that you can do this on your own. All right, we're back. So here's my great artistic ability. So this is minus, so remember V stop is positive, so this is minus V stop. The fastest electrons are being stopped, right? So there's no current, because the current is the flow of electrons. And then when delta V is negative, you know, so this is V stop, or negative V stop, so the current's increasing, 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 and then eventually it's just going to get constant. Okay? So that, I mean, go through everything that we discussed, but that's it, right? Now look at here. So here's the voltage is 0. So some of the electrons are escaping, but they're going at different angles. So here we just have a little bit of positive voltage. So that means that pretty much all of the electrons will hit that anode. And then since the temperature doesn't change, the current is constant. So that basically just summarizes everything that we've talked about. So I hope that makes some sense to you. Okay, now do the same thing, but now draw the graph after the cathode temperature has been increased significantly. So what's the big deal there? Well, remember, classically, how do you eject electrons? By heating this thing up so the electrons' thermal energy increases and they have enough energy to overcome the work function, right? So pause your video and draw the curve. Okay, so here it is. So the only thing that's different, I mean, obviously you can have more and more electrons, right? More and more electrons, so that means you're going to have a higher current, right? But also, you know, since the thermal energy is, this is constant, this just depends on the metal, you know. So this is increased significantly, so that means that the kinetic energy of the electrons is increased significantly. That means it's going to take a greater V stop, right, to stop those super fast guys. So it's just basically the same curve, just with a whole lot more electrons and a whole lot more energy. Okay. All right. And again, that's classical physics. And that's a good time to stop. Okay, let's stop that one.